As I look at this integral and I think about how I would go about evaluating it, you may jump to the conclusion that we would use trig substitution because we see this square root and this x squared plus 4 much like things we've been dealing with. But hold on a minute. Sometimes when we know too much, we try harder things than are necessary. It turns out for this one, u substitution will work nicely, and that's because we have this function of x here. So if we let u equal x squared plus 4, then du is going to be 2x dx, and we could divide both sides by 2, and we would have 1/2 du equals x dx. And so we know it's going to work nicely because we have the x dx that we need for this substitution. So the x dx is going to be 1/2, we'll put that out in front, du over the square root of x squared plus 4, well, that was just u. So this can be written as 1/2 integral of u to the minus 1/2 du. So we have this down to something that we can integrate. And so we're going to have actually just u to the 1/2 plus a constant. We can see that this would work because if we did a power rule, power out in front, that's where this 1/2 comes from. Decrease the power by 1. There we go. That plus a constant looks a little high. We'll move that down. Plus a constant. Now let's go ahead and resubstitute, and we'll go ahead and resubstitute also writing it back in radical form. So u was x squared plus 4, and then we have plus a constant. Let's just do a quick check of this. If we have x squared plus 4 to the 1/2 plus a constant, and we did a derivative, the constant would go to 0. We would do the power out in front. We would decrease the power by 1. And we would multiply by the derivative of what's inside. And you can see that this will check out because the 2's would cancel, and then this would go to the bottom and we could write it in radical form, and there we have it.